Hey all, um, good evening. I'm Arjun. I hope I'm audible to all of you. Please put out, take a few, please have thumbs up. Great, great. Yeah. Oops. Good evening. I'm Arjun. I hope. Yeah, sorry about that. Cool. I hope you all had a great first session by Sanket. You must have enjoyed it, I hope. Let's wait for maybe a minute or two for others to join, and we'll start on with the second session. Right. So how did you like Sanket's? How many of you attended Sanket's session? I hope all of you did. Nice. And was it helpful for all of you? That's very good to know. Great. Yeah, you have a plethora of topics lined up for the next couple of days. Yeah, we hope you make the best use of it. We have some very good educators lined up. Hope you make the best. You should enjoy it and take up the opportunity. Yeah. Amazing. Okay, I hope everything is fine for people watching on YouTube as well. So let's dive in, right? So in the first session, you saw a lot of different programming constructs, right? And the second session is kind of the next fundamental topic, I would say, which is called complexity theory. It's a very fancy word. It sounds literally it sounds complex, but it's actually not that intimidating a topic. What it really means is just analyzing your program, right? Figuring out whether your program is correct, figuring out whether one program is better than the other program, and how exactly do you go about doing it in a very quantified way. So let's dive in, right? So that is what is called computational complexity theory. It's a mouthful, but please don't get intimidated. And as I was saying, it's nothing but figuring out whether one program is better than another program, or just given one program, how do you make it better, right? It's yeah, right. Bapi, that's true. It'll be better if it's more than 1 hour. So from tomorrow, the sessions will be for 2 hours. Today, because we could start only in the evening because it's a weekday, it's just for 1 hour. But in the coming days, we'll have it for 2 hours each. And but this being a fundamental, it's kind of like a basic topic. I don't think it requires more than an hour. If something does spill over, we'll continue from tomorrow as well. Don't worry about it. Yeah, great. So resuming. So computational complexity theory, right? So there are lots of variants to this, but what we generally look at when we are doing any computative programming, or in general in most practical purposes, are just two main complexities which we look at, which is one is time complexity and the other being space complexity, space or memory complexity. So what does this mean? So time complexity is pretty simple. You write a piece of code and you want to figure out how fast it runs, right? And this is very simple to do. You just run it and you measure the time it takes. So what's the big deal about this? One, it is hardware dependent, right? So one program I write, I might have a supercomputer, or I might have my laptop, which is super bad, which I'm sure is the case with a lot of you. So the time itself is going to be different based on where you run it. So that's not a very deterministic metric. So we want something pretty robust and pretty deterministic. So there's a very simple next step, which is don't measure the actual time. We know that the time is basically very proportional to the number of steps that is taken by the program, right? If I have a program which runs for 10 steps and one which runs for 100 steps, I know that no matter which computer I run it in, the 10 steps is going to run faster than what a 100 step thing is going to run into, right? So don't measure the actual time, measure the number of steps it takes. Am I not audible? Is this the case for everyone? Okay. Okay. So I think some of you might not be hearing me. Maybe it's just your volume. Just try increasing your volume. I think it's audible for most people. Great. Sorry. So coming back. So instead of measuring the actual time, we just measure the number of steps that it takes, right? But please be very careful that the number of steps that a program takes is not the number of lines you write in a code, right? It's the number of steps it runs in execution. We'll come to this point again in a few slides. But so again, this is also very simple, right? So let's just take one example and see what happens. Bishnudev, this chat that I'm looking at is on Unacademy. I'm not looking at Discord or YouTube right now. There are other people answering questions there, but I am mainly looking at the Unacademy chat. I'll not be able to look at all questions which are being asked even on Unacademy, but I'll try to look at the chat box now and then. Yeah. So okay, so let's take one simple example, right? So this is a C++ code, but I hope the code is simple enough that even for people who use Java or Python or whatever it is, it should be easy enough. The only thing you need to know is that Cin is input, Cout is output, right? So what we have here is a code which has three variables, which are integers A, B, and C, and you take in the integers A, B, and C, and you have another variable called sum, and sum just adds each variable one by one. So if I have A as 10, B as 20, and C as 5, then sum will be 0, then sum will become 10, then 10 plus 20 will become 30, and then 30 plus 5 will become 35. And it will output this sum at the end, right? So it's a very simple code, which basically takes three integers and tells you the output of these three integers. So now, if you want to analyze the time complexity of this, the simplest thing we're going to do is find how many steps it takes, right? So if you want to look at that, so here it's one maybe, right? So this is one step. This is another second, 3, 4, 5, 6, 7, right? So this is just 7 steps. Okay, so this operator, don't worry about it. It's just input, and this is just output. This entire C in, C out, just think of it as input and output. Don't worry about it, right? So the number of steps this code has is just 7 steps. There's nothing more deep about it. There's nothing to analyze, right? So we just say, okay, 7 steps. No matter which code it is, which computer it's run on, it's going to take 7 steps. The actual time might differ very slightly, but that doesn't matter to us. It's 7 steps. Great. So what's the big deal, right? But now let's look at another slightly different example, which does pretty much the same, except that it's slightly more general. What do I mean by general? Let's have this example, right? So in the last example, we had 3 integers, but now we have this code which doesn't have just 3 integers. It takes n integers, where n is a variable, right? So n is an integer which is taken from the user, and then we input n integers, whatever the user wants. Maybe the user wants the sum of 3 numbers, maybe the user wants the sum of 100 numbers. Whatever it is, the user first tells us how many numbers he wants the sum of, right? So think of it as a calculator. It's like a simple calculator, right? In a calculator, each time you have to do 5 plus 10 plus 15, whatever it is, right? But instead, this is a slightly different calculator where you first enter the total number of integers whose sum you want, and then you enter each integer one by one, right? That's all this code does. It has this array which can store up till 10,000. So any number less than 10,000, it can any number of integers less than 10,000 it can manage, and then it takes in the number of integers, and it takes in each integer one by one. N such integers it takes it, and then I have this variable sum, which, sorry, one second, maybe I should, yeah, and it has this variable sum, and it goes through every element in the array and adds the values one by one, and then finally outputs the sum, right? So if I have 4 integers, I'll input 4, then I'll input 2, 5, 1, 6 maybe, and then the final answer is going to be 2 plus 5 plus 1 plus 6, which is 7 plus 8 plus 14. So the final answer is going to be 14, right? It's a very simple piece of code. But now, what is the time complexity? Or like if I want to analyze the time complexity of it, what did we discuss? We said we look at the number of steps it takes, right? So right here, it should be clear that the time, just measuring the time is not going to work, right? Because that even on the same computer, this piece of code will take different times to execute depending on the input, right? I have my input as 42516. It will take some amount of time. If I have another input which is like 400 and I give 400 integers, it's going to take slightly longer time to execute and give the output, right? So here itself is one, just a question. How do I know what is the holy grail? What is the input which I should give? I don't know, right? And you see that this same issue occurs even when we look at number of steps, right? Because now what is the number of steps that are executed when this code is run? So here, one step. This is second step. But here, you see that the number of lines is just 2. The number of lines of code is just 2. But what happens when you run this code? It will go into this loop n times, right? Because that is what a for loop does. This is for loop in I think most languages. So I hope you know what a for loop is. It just loops, it iterates over the same line again and again and again. And just the variable I changes. So it takes in different at different places of the array, it keeps placing the integers. But how many times this is run? It runs n times, right? It 1, 2, 3, 4 until I becomes n. So that n times this line is executed n times, right? So here we had one step. This is one. This is another step. This is n steps. This is just one step. Again, this is run n times, right? Because it's a for loop and sum goes and adds each and every element one by one by one. So there are n steps here and it's outputted once, right? So what is the number of steps this has taken? It is 1 plus 1 plus n plus 1 plus n plus 1. So when n was 4, this would be 2, 6, 7, 11, 12. 12 steps. This would execute in 12 steps. But if n was 400, the number of steps would be 400 plus 400, 800 plus 4, 804. Yeah, this would be the number of steps. But then now how do I know what to take, right? When I want to just have a piece of code, how do I know the number of steps it takes without knowing what the input is, right? The input doesn't come with the code. The input is given with the user, right? So, okay, so the reason 10,000 is taken is just a random upper limit. I can have whatever I want. I just decided on keeping just 10,000 numbers and not more than that. There's no specific meaning behind 10,000. Yeah. So here again we fall into another issue, right? So our thought process, which was that to measure the efficiency of a code, we look at the number of steps, falls apart here because the number of steps is not a fixed number, but it depends on the input, right? As opposed to the previous code, here it didn't depend on anything. It was fixed. No matter what I give as A, B, and C, it will always take 7 steps. I can give A, B, and C as different values. I can give 5 plus 10 plus 100 or 1 plus 1 plus 1. Whatever it is, the number of steps is going to be 7, right? But here, the number of steps itself, the output here depends. In the first example, the output depends on the input, sure. The second example also, output depends on the input. But then in like more than that, the number of steps also depends on the number on the input that I give, right? And this is something which is kind of very critical to the entire sphere of computer science and algorithms. In general, algorithms, these are the kind of problems which we'll almost always see. You'll almost never come across or study an algorithm which has a fixed number of inputs. It'll almost always be I give you some integers, sort them in ascending order, or I give you some n number of integers, find the sum of all the numbers, or find the maximum of all the numbers, or whatever it is. Different questions are asked. It'll almost always be, you'll almost never find problems which say, I give you 5 integers, do something with it. It'll always be, I give you n integers, do something with it, right? And why is this? This is again one of the important advantages of having a code, right? So why do we write a code? So one of the advantages, one, it's fast. Computers are fast. Second is reusability, right? We write one piece of code, and for various inputs, the same code can be run on it, right? Otherwise, it's a one-time use code, which is not very useful, right? So depending on the input and the size of the input, the number of steps changes, and this is where we come to the actual time complexity concept, which is we see that the number of steps here, if we write down actually, is 1 plus 1 plus n plus 1 plus n plus 1, which is nothing but 2n plus 4, right? So the number of steps is now a function of n, right? So it is like the function as in the mathematical function. I don't mean the computer science function. It's the mathematical function which you have seen in high school. F of n, f of x, f of y, polynomial. You must have seen those things, right? Remember that. And now you see this 2n by 2n plus 4 is basically a function of n, right? So f of n is 2n plus 4 is the number of steps. Rishabh, that's a very interesting question you ask. Why chats are disabled? They're not disabled. I mean, you literally just asked you literally just chatted now. I'm not sure what exactly you're saying. Sorry. Yeah. Right. So coming back. So now as we see, the number of steps is a variable, and this is kind of the whole concept behind time complexity, right? So how is it 2n plus 4? 2n plus 4 is just, look at this example. This is one line. This is one execution. This is second execution. This line is executed n times because it's a for loop which runs from 1 to n. That means n times. This is run once. This is again a for loop, and so this line is executed n times, and this is one. It's executed once. So the total number of times, total number of lines which are executed, this is n plus n, so 2n, and 1, 2, 3, 4. So 2n plus 4 is how that comes up. So I hope that's clear. Right. So yeah, sorry about that. So now what we have here is a runtime defined as a function of n, and what n here is basically, n is kind of the number of integers which are given, right? So it's kind of like the size of the input. If I give 2 integers, my input is going to be just, I don't know, some 5 and 10, which is small. If I give 100 integers, my input is going to be large, right? So the larger input I give, the more time it takes. The smaller input I give, the smaller time it takes. So it's kind of dependent on the input size, right? So this has a very important theoretical background behind this, the concept of input size, but we'll not worry too much about it. So I'll just mention it here. So input size is something which is very crucial when you look at this from a very theoretical point of view. And input size is usually measured in number of bits. Okay, so it's like the number of bits in the input that you give. But this is a very theoretical part of it, which we'll not go into. Instead, we'll just consider the number n, right? So if there are n integers, we take the input size to be n in a sense. Okay, so it's usually that most of these codes take an array as an input. Or maybe 2 arrays or 3 arrays, most of which are equal length or something. So we'll usually look at just this n and not actually go into the deeper detail of how many bits are needed, right? So we'll cover just number of integers is n in the input, and so now we have 2n plus 4, right? So this is most of what we call as time complexity, right? So now you see that this code takes 2n plus 4 number of steps, no matter which computer it is run in, no matter what input I give, whatever n is in that input, the number of steps is going to be 2n plus 4. It's a very clean way of telling me what my how fast my code runs, right? So I have one code which is 2n plus 4. Maybe I have another code which is 5n plus 6, right? It's pretty obvious that 2n plus 4 is always less than 5n plus 6, right? So I can say this code is faster than the second code, right? So if I have a problem and I have two different approaches, one approach which takes 2n plus 4 time, 2n plus 4 number of steps, and another which takes 5n plus 6 steps, but both of them give the correct answer always. I mean, we are not comparing codes and programs which have different output, because then the correctness itself goes for a toss. We always assume that we are comparing two programs, both of which are correct, but the number of steps it takes differs, and we basically want to find out which is faster in a sense, right? And it's in this case it's pretty obvious that 2n plus 4 is faster than 5n plus 6, right? It's just simple arithmetic. It's just a simple algebra. 2n plus 4 is always less than 5n plus 6. Great. But what if I have a code which takes 2n plus 400 steps, right? And another code which takes 5n plus 6 steps. Okay. Which of these two do you think is faster? It depends on n. Okay. Some people think it's 5n plus 6. Some people think it's 2n plus 400. It's not 2n plus 4. It's 2n plus 400 now. Yeah, I've changed the statement. I'm just saying basically, suppose I have a code which I've written, which have a lot of single statements, like 400 different single line executions, and I have two for loops of n. So that will be 200 plus 400, 2n plus 400 number of steps. And I have another piece of code which has 5 n loops and just some 6 single line statements written somewhere, right? So which is faster? And both of them give the correct answer. But now my question is, which program should I use if I care about speed, right? Okay, some of you say second one. Okay. Okay, so let's just do a simple algebra, right? So let's say 2n, so n is a variable, right? So let's just consider this as a algebraic inequality and see what we get on the bounds of n, right? So we have 2n plus 400. Suppose we want this to be less than 5n plus 6. Okay, then just treat this as normal algebra. I'll take this 2n and throw it to the other side. So 5n minus 2n will become 3n, and I'll take this 6 and I'll throw it to the other side. So 400 minus 6, I'll get 394, and I have this inequality sign here, right? And I'll take this now 3 and throw it this side. So I get 394 by 3 should be less than n. So I basically have n should be greater than 132 or 31. Yeah. So if n is greater than 132, that is the number of integers I give is more than 132, then 2n plus 400 is going to be less than 5n plus 6. But if not, say n was, I don't know, 2, right? So let's just throw in n equal to 2. What does this evaluate to? This evaluates to 2 into 2, 4 plus 400. So I get 400. On the other side, I get 5 into 2 is 10, 10 plus 6 is 16. So obviously 400 is greater than 16. Yeah. Similarly for n equal to 3, again 2n plus 400 is going to be larger than 5n plus 6. So n equal to 4, n equal to 5, all the way up till n equal to 131. 2n plus 400 is going to be larger than 5n plus 6. But take any n which is greater than 132, and math tells us that the left hand side is going to be smaller than the right hand side. Yes, I hope this math is clear. It's just, there's nothing deep about it, just rearranging the terms. Why does this happen? Let's look at a simple way to see what is happening. And what we're going to do is we are basically going to plot this. Again, high school math, graph, right? So x-axis will be n and my y-axis will be f of n. In this case, first we look at f of n as 2n plus 400. Yeah. So this is 0, 0. So when n is 0, what is f of n is 400, right? So n is somewhere here, right? So it starts out from here. And when n is 1, I'm going to get 400 plus 2, so 402. Then when n is 3, I get when n is 1, I get 402. When n is 2, I get 404, then 406, and so on. So I'm basically having a line like this. Yeah. But now on the same graph, we'll plot another y-axis where we'll take g of n is 5n plus, what did we decide? 5n plus 6, right? Yeah, 5n plus 6. So let's plot g of n as, okay, maybe I should use a different color. My bad. This is f of n. Yeah. Now let's take g of n in red. And g of n is nothing but it is 5n plus 6. So when n equal to 0, g of n is 5n to 0 plus 6, which is 6, right? So 6 is somewhere down here. Yeah. Then we get when n equal to 1, we get 11. Then n equal to 2, we get 16. N equal to 3, we get 21, and so on, right? So the line is going to look something like, I'm very bad at drawing. I think there is some line drawing tool as well, which I have not looked at yet. But the point being, the slope of 5n plus 6 is larger or steeper than 2n plus 400. Yes, because what is slope? Slope is, if you remember again your high school math, we have two equation of lines, y equal to mx plus c. This m was the slope, right? The larger the slope, the larger the m. I mean, it's going to be as close to the y-axis as possible, in parallel to the y-axis. So m equal to 0 is y equal to x plus c, which is basically parallel to the x-axis. And m equal to infinity is kind of like the y-axis in some sense. Yeah. So I hope you remember this from your high school math, high school whatever. So basically this g of n has a steeper slope than f of n. But it starts out from a smaller value. This c is smaller, so it starts out from a smaller number, but it grows faster than f of n in a sense, right? So yeah, we are finally using y equal to mx plus b. Your high school math does come handy sometimes. Yeah. So as you see, at some point this red line is going to cross the blue line. And where does it cross? As we saw, the math basically tells us that it crosses at n equal to 132 or 131, between 131 and 132. Yeah. So and after that, the red line is always going to be above the blue line in a sense, right? And this is kind of the starting of what we call asymptotic analysis. Okay. So what do we mean by asymptotic analysis? It basically tells us, okay, I should maybe write it down. Asymptotic analysis. Again, a very intimidating word, but it's actually not that hard. Let's kind of break down what it means. All asymptotic analysis says is, don't worry about smaller inputs. Okay. Worry only about larger inputs. What is the funda behind this? Our computers are very, very fast, right? They are so fast that they can run up till something like 10 power 8, 10 power 9 steps per second, modern computers. And there are supercomputers which are even much faster than that. And this number keeps increasing almost year by year. So when we are looking at some small numbers of n, right? All the numbers of n we've seen so far, even like 132, the number of steps is like hundreds or thousands, right? So it's going to take less than milliseconds to complete these number of steps. Yes, because 10 power 8 steps can be done in 1 second. So something like 1000 steps is done in 1000 by 10 power 8, which is like 1 by 10 power 5, 10 power 5th of a second, right? So the difference between the actual times when the input is very small is going to be almost negligible. How does it matter if my code runs in 1 millisecond or it runs in 2 milliseconds? I don't care much, right? But what I care is what happens when the input grows very large, right? Because then a difference between 1 hour and 2 hours is very important for me, correct? The difference between 1 millisecond and 2 milliseconds is just 1 millisecond, which I don't care about. But the difference between 1 hour and 2 hours, it's the same proportionality, right? So 1 millisecond into 2 is 2 milliseconds. So 1 hour into 2 is 2 hours. But the difference between 1 hour and 2 hours is huge. Even though proportionally they are same, the difference between them practically is humongous. I would much prefer 1 hour than 2 hours, but I'm fine with 2 milliseconds rather than 1 millisecond. So if I have a code which on small input runs in 2 milliseconds, but on large input runs in 1 hour, yeah. But I have another code which runs in 1 millisecond, so it's faster in small input, but on larger input it takes 2 hours. Then the choice is obvious, right? I'm going to choose the one which takes 1 hour rather than 2 hours, even though here I'm compromising and giving 2 milliseconds. I don't care about it, right? So this is kind of, so this is not the, I'm not being very technical here. This is just a kind of like a very hand wavy intuition as to why asymptotic analysis is what we consider. And this is kind of what asymptotic analysis says. Don't worry about small inputs. Worry only what happens when the input becomes large, okay? So this is the whole concept behind asymptotic analysis. So now going back to the previous slide. So now when we have 2n plus 400 and 5n plus 6, it should be pretty obvious that I'll prefer 2n plus 6, 2n plus 400. Even though in smaller numbers, 2n plus 400 is worse, when n becomes large, when n is say some 10 power 8, this is going to run in 2 hours, whereas this is going to run in 5 hours. It's going to run in 2 hours plus some minuscule amount. This is going to run in 5 hours plus some smaller minuscule amount, but I prefer 2 hours, right? Even though on smaller numbers, this probably runs in like 10 milliseconds, whereas this runs in 2 milliseconds. I'm fine with having that trade-off, but on larger input, I want my program to run fast, because that is where the actual difference practically matters, okay? So this is the whole concept behind asymptotic analysis. So there's a very structured and formal way to write down what these things mean. Maybe I'll just very quickly write it down, but you don't need to worry too much about it if it's not very clear to you. So we say that f of n is, let's say, better than, I'll make these things a bit more formal in a while, but we'll say f of n is better than g of n if there exists, so okay, maybe if you're not familiar with this notation, this just means there exists an n naught such that for all n which is greater than n naught, I have f of n is less than g of n. This is not the whole asymptotic analysis, we are going step by step, but this is the first step, right? So is this kind of clear? I have an n naught. Here in the previous example, my n naught was 132. So for all n which is greater than n naught, which is greater than 132, 2n plus 400 is less than 5n plus 6. But for things less than 132, it's the other way around, but I don't care about it. I just want some cutoff such that beyond that cutoff, f of n is always smaller than g of n, right? In that case, I don't worry about what happens here. Here it might be chaotic. When n is small, it might be very chaotic. I don't care about it. But after a particular point, my f of n is always less than g of n. Let's say less than equal to. Right? These things don't matter so much, right? In this case, I'm going to say f of n is asymptotically better than g of n. Okay. This is still not the full, there is one more very important step, we'll come to that, but this is kind of the first step of asymptotic analysis, right? We don't care about small inputs, we care only about large inputs. Got it? Cool. So now we go to the kind of the second step. So okay, so let's again here. So in some sense, the graph of f of n and g of n would be like, I have f of n, it might be some chaotic thing, but after, and similarly my, so this is g of n and my f of n is something like this, say. So this is f of n and this is g of n, but so, and this is n naught, yeah. So before n naught, that is before 132 in the previous example, it's chaotic. My blue line might be greater than my red line, or it might be less. I don't care about it. I just don't simply care about it. In the worst case, my blue line is larger than the red line. Fine, let it be. But after n naught, my blue line is always lesser than the red line, right? And this basically tells us that for all n greater than n naught, f of n is less than g of n. Because it's lower, f of n is less than g of n, yeah? And this is what we want. So this basically means f of n is asymptotically better than g of n, right? And we'll, and given two programs, we'll usually prefer f of n over g of n, because for larger inputs, f of n is better than g of n, okay? What is this endpoint? How do we calculate it? That's a very good question. So in this example we saw, right? So we calculated, so this was f of n and this was g of n, and we basically did a math equation. Where is it? Yeah, right. We basically did a inequality and we got n is greater than 132. So that's our n naught in that case. Right? It might not always be this simple, figuring out what that n naught is, but it's usually just some algebraic manipulations. You throw things around, you do some algebraic trickery, and you'll usually get this. It's usually not very deep, and you'll never ever do this in an actual contest or when you're doing an actual proof, because as you'll see, this becomes very intuitive and very obvious once you go to the next step. We wouldn't care about these things at all. Okay, I will get to that in a minute. So great. So now we come to the next step, which is, say I have f of n is the same thing, 2n plus 400. That's huge. And say okay, this was actually blue, right? F of n is 2n plus 400. And now I change my g of n and I say g of n is n square. Okay. So earlier we had two linear equations, right? I hope you know what linear and quadratic mean. So now we have a linear and a quadratic equation. Yeah. So now why is this important? So now let's try to analyze these two functions. Again, if we draw the graph, how is f of n plus 400 going to look? As we saw, it's going to look something like this. Yeah. Where this is at, it's going to start out at 400. When n equal to 0, f of n is like this. But now how is g of n going to look? G of n at 0 is 0. At 1, it is 1. At 2, it is 4. At 3, it is 9. At 4, it's 16. Right? And what is this shape going to be? How is g of n going to look like? Again, high school math. Yes, it's going to be more steeper, but is it even going to be a line? Correct. All of you are perfectly right. It's going to be a parabola, right? Semi-parabola, sure. If we consider negative numbers also, it's going to be a parabola, right? So it's going to look like this. Yeah, I didn't draw based on the dots, but it's basically a curve steeping up, right? So it's not just steeper than the f of n. Its slope increases as you go down the line, right? So that's what quadratic is, right? Your slope is also a variable, if you again remember your 11th, 12th, it's like if you differentiate it, you get the slope, and then that slope itself is increasing with time, right? So it's not just going faster, it's also accelerating, right? So the physics equivalent is n squared is faster and it's also accelerating. So the more you go, it grows even faster, right? Whereas 2n plus 400 is a steady speed. Its speed remains the same. It's always 2, right? The slope is always 2, right? Whereas the slope in n square is 2n, right? If you differentiate it, you get 2n. So slope is at the beginning low, but then it increases, and at some point it grows super high, and it grows beyond 2, and the value also grows beyond 2n, beyond 2n plus 400, right? So again, what is the main point we want to take away from this? The main point being n square, even though it starts out low, very low, it very quickly surpasses 2n plus 400, and after that it's going to grow much faster than 2n plus 400, right? And let's also plot 5n plus 6, right? So 5n plus 6 was something like this, probably. Must have probably been like this. Yeah. Again, 5n plus 6 is worse than blue, but n squared is worse than both of them, and it's worse in a much worse way, right? If that makes any sense. And why is this thing? This is again because of the slope being not a constant. It grows. The slope itself grows, right? It's acceleration, blah blah blah. And mathematically, what is it all like? I mean, like very practically speaking, what does this all boil down to? It just boils down to the fact that f of n and 5n plus 6 were linear equations, linear polynomials, whereas g of n is now a quadratic equation, right? You can be pedantic and say, okay, the quadratic equation can even be a downward parabola, and so it goes down, and so on and so forth. But then know that the equations we are looking at here are all equations on the number of steps, right? And the number of steps are always positive, and the number of steps typically grow larger as the input grows, right? So we will make these all like some kind of like simple assumption, so that just life is easier. So quadratic is always worse than linear, right? And that's the whole point. No matter what linear equation you take, right? I could take 100n plus 10,000, yeah, and I could take the simplest quadratic equation, which is n square, right? Not 2n square, not 5n square, not 100n square, just the simplest n square. I could even have n square minus 10,000, right? It's even like kind of smaller than, in a sense, smaller than n square, but still 100n plus 10,000 is better than n square minus 10,000. So even because minus 10,000, all it does is it starts from it'll start from negative, right? But it'll soon catch up, because again, being the parabola it is, it'll surpass a line almost literally always, right? And that's the whole point. Quadratic is always worse than linear, no matter what the multiplying factor is, no matter what this 2n is. It might be 5n, it might be 100n, no matter what it is always going to be worse than linear. Okay, so this kind of brings us to the next point, which is, given that we know we care much more about our algo being linear rather than a quadratic, and similarly we are so much better if our program is quadratic rather than cubic, right? I would much prefer having 5n square plus 10,000 rather than having n cube. Yeah, this is the same logic, because n cube again accelerate much faster than any n square, right? Similarly, a cubic is always better than a power 4, and so on and so forth. And in a sense, any of this is better than 2 power n. Okay, 2 power n is your exponential, which grows literally exponential, right? I mean, it's the English word exponential which we use, right? It's explosive, exponential, right? It grows super fast. It's n power 100 is also better than 2 power n, right? Because at some point, 2 power n is going to is going to overtake your n power 100. If you want the actual math behind this, the math is just to actually differentiate and then find out where exactly they lie. And when you differentiate, you see that the slope of 2 power n will be much larger than 100 n minus 1, whatever it is, 100 into n power 99, right? So all this kind of loops back to the math background that we looked at, the foundation, but we'll never go into that, right? For us, it's very simple. Linear is better than quadratic, which is better than cubic, which is better than power 4, and all of these are better than exponential, which is 2 power n or 3 power n or 4 power n, any of these things. Those are the worst for us. Whereas linear is the best, quadratic is like, okay, I'm fine with it. Cubic is usually and 2 power n just I don't want to go anywhere near 2 power n, right? And this is how things work out in most of our problems. There'll be some problems in which you have to do 2 power n, but then the input will be super small and will be like 10 or 20, in which case you can go for exponential, but those are relatively, I wouldn't say they're very rare, it's relatively uncommon, whereas most of the bulk of the problems will be in some what we call polynomial solutions. Polynomial is just linear or quadratic or cubic or any of these. N power c are polynomial. Okay, so given all this, what we basically say is that given that I know that I always prefer linear over quadratic, do I really care that much about 2n plus 400 or 5n plus 6 is the question, right? I have 2n plus 400 and I have 5n plus 6. Both of these are linear. I know that we talked about this and we know that 2n plus 400 is actually better than 5n plus 6. But then when I'm looking at it from the realm of other polynomial solutions like n cube, like n power, like n square, both of these are almost equivalent, right? I mean, sure, it takes 2 hours and 5 hours, but it's still in hours. Whereas if I go to n square, it's going to go into days or probably even years, right? So the difference between 2 hours and 5 hours now in this realm becomes very insignificant in a sense. Okay, so from that perspective, we'll basically say, okay, I really don't care about whether it's 2n plus 400 or 5n plus 6. All I care about is it's linear. Okay. Similarly, I don't care if my algo is n square or 3n square plus 30 or whatever it is. It's quadratic. That is what I'm most worried about. Okay. And similarly, I don't care about difference between cubic. I just care it's not exponential or it's not n power 4. Right. And this brings us to the second most important point of complexity of asymptotic analysis, which is the multiplier c, constant c, right? So I have f of n, I have something, right? I'll multiply it with any constant c, okay? So basically, I don't care if it's 2n plus 400, I'll multiply it with say 2.5. So 2.5 into 2 will give me 5, right? So I get 5n, right? So I don't care about it. And I'll add any other, say c1, and I'll add any other constant c2, right? And I don't care about it. I say this is kind of equivalent in our current universe to f of n. Okay, so f of n is equivalent to c1 into f of n plus c2. So n and 2n plus 400 are the same. Why? C1 is 2, C2 is 400. And similarly, this is also same as kind of equivalent in a sense, right? To 5n plus 6. So now, and similarly, these two are also equivalent, right? Because how do I take this and convert to 5n plus 6? I'll probably just multiply by 2.5 and then subtract some 394 or something. I don't know. So something, right? You can figure that out. I'll have some C1 and C2 such that I can convert 2n plus 400 to 5n plus 6. Right? So I'm kind of creating like an equivalence class where all these functions, yes, I can say that some of them are better than there, but they're mostly the same, right? That there's not a huge difference between them. And this is our entirety of complexity of asymptotic analysis, right? So, but the point is, if I start out with n, I can never reach n square doing this, right? because I can always do only multiply by a constant. I can't multiply by a variable, right? So if I have n, I can multiply by c1 and add a constant c2. So I can get 2n plus 400, I can get 5n plus 6. I can never get n square. So n and n square will never be equivalent, right? That's the whole important point. And similarly, I can start from n square and I can get 2n square plus 5. I can also get 2n square plus 100n plus 1. This I can not exactly like this, but something similar to this I can get. But I can never get n cube, right? Because for that I need to multiply by a variable. N square into n is n cube. So I can't multiply variable, I can only multiply by constants. And that's exactly 2n minus 400 is equivalent to n totam. Yeah. So now going to the next point. So now that we have this, now we are equipped to answer our initial question, which is, okay, I have one code which takes f of n. I have another code which takes g of n, yeah, which is better. And this is where we come to the concept of big O analysis. Yeah. So let me first kind of write the somewhat formal notation of big O analysis. So we say that f of n is big O of g of n if there exists C1 and C1, C2, and let's say n naught. I'm being slightly easier, it doesn't have to be so much, such that for all n which is greater than n naught, C1 f of n plus C2 is greater than or equal to g of n. Okay. Does this make sense? So it's kind of like we are clubbing the first and the second steps. What was the first steps of first point of asymptotic analysis? It was we don't care about small numbers, right? And that is what we say by here. For all n greater than n naught, we don't care about what happens in the smaller n. We care only about larger n. And even the larger n, we don't want a strict less than. We are fine with doing this constant multiplication, right? We are fine with adding a C1 factor. Even then we are fine with it. Even after, I mean, I have f of n and I have g of n. Even I'm fine with, if I have f of n is 2n, I don't mind changing it to 5n. But I don't want to change it to n square. I don't mind changing it to 5n, right? It's a constant multiplicative change we make. And after making that multiplicative change, sorry, this should be less than, my bad. Yeah. So after that, after doing both, if I get f of c1 into f of n plus c2, this is usually not needed, is less than or equal to g of n, then we say that f of n is in a sense better than g of n, or it's not worse than g of n, is what we usually, it boils down to, right? And this is big O notation. Okay, so f of n is, this just kind of usually means less than or equal to in a very vague sense. Where this less than or equal to has a lot of nuances poured into it, but practically speaking, this is what it boils down to. That is, f of n is kind of better than g of n in a sense, which is f of n is less than or equal to g of n. So g of n is like an upper bound on f of n. Okay. So why is it O of g of n? Yeah. So this O of g of n is kind of the notation we use to say it's less than or equal to, right? So it kind of packs in all this extra 2 points inside it, which is, for smaller n, it might not be the case that f of n is less than or equal to g of n. It might be different. And similarly, there might also be a multiplicative factor difference, right? And that's why that these are the 2 points which are kind of poured into this notation of big O, right? And the reason why with this is all what we covered so far. Kind of the intuition behind why this is the definition of big O is what we covered so far. I hope that kind of motivates why this is the reason big O notation is defined like this. All we talked about till now is basically to to get you to understand why this is the definition of big O. Right? It's not just a magical definition with some. Sorry, 1 second. Yeah, it's not a magical definition with some mathematician or some theoretician gave. It's actually based on real life practical usage, right? And that's big O notation. So now let's quickly look at some examples, right? So the first example is obviously 2n plus 6 or 2n plus 400 is big O of 5n plus 6, yeah, because we can convert 2n plus 400 into 5n plus 6 by just doing this. And similarly, 5n plus 6 is also big O of 2n plus 400, because we can just multiply it by into 2 by 5 and it will become 2n plus 6, right? So big O, because it's equal, so everything in that equivalence class that we talked about, everything will be big O of each other, because they're kind of like equal in this new realm that we are in, right? But more importantly, 2n plus 400 is big O of n square. So n square is an upper bound on 2n plus 400. It is also big O of n cube. It is big O of 3n square plus 6 or whatever it is, right? But it is not. I cannot write that n square is big O of 2n plus 6. See, this is where big O doesn't work, because 2n plus 6 is never an upper bound on n square. It's only the other way around, right? So big O notations are always upper bounds. So n square is an upper bound on 2n plus 6, right? But it's a large upper bound. What we would usually go for is 2n plus 6 is big O of n. And this is the main usage that we see practically, right? So big O is an upper bound, but what we usually say is kind of like a tight upper bound, okay? It is also big O of n square. It is also big O of n cube, because big O is just kind of like upper bound. But I mean, if it's big O of n, it's obviously big O of n square. Some function which is big O of n is obviously a big O of n square as well. It's obviously big O of n cube as well. So to make our statement just as precise as possible, we'll usually say it's big O of n and not big O of n square, right? So coming back, so something like 2n square plus 5, is it big O of n square? Yeah. Correct. It is big O of n square. Is it big O of n cube? No, Lakshit, it actually is big O of n cube, because remember, what is the takeaway? Big O is kind of upper bound. N cube is an upper bound on 2n plus n square. N cube is larger than any quadratic, right? So it is still big O of n cube. It is also big O of n power 4. But these two guys are kind of redundant, right? We don't care about them. I mean, yes, it is true, but I mean, it is big O of n square. So if some value is less than 100, it's obviously less than 500. It's obviously less than 10,000 as well. But we usually just say it's less than 100 and stop there, right? And that's kind of what we say. Yes, it's big O of n square, and we usually stop there. We usually don't say it's big O of n cube as well, even though technically it is correct. Theoretically it is correct. We don't say it. But the other important question is it big O of n? No, right? Perfect. So all of you are absolutely correct. 2n square plus 5 is not big O of n, right? Similarly, 3n cube plus 5 is not big O of n. It's not big O of n square, but it's big O of n cube, right? So any random polynomial I could take 4n cube plus 5n square plus 6, right? This is big O of n cube, but it is not big O of n square. It is not big O of n, and it is not big O of 1. Yeah, this is correct. big O of n square, it is naught, because it's n cube, right? N square is not an upper bound on n cube. Yeah. And this is the important part, right? So when you look, let's go back to the very first point that we're talking about. Like, where did this all start from? This all started from the number of steps that your code takes, right? Screen is not visible. Is that the case for everyone? No. Okay. So Vedant, I think it's some issue with your maybe just try refreshing. So where does this all tie back to, right? So let's go back to the very first point that we talked about, which is let's kind of reiterate what we looked at, right? So where did we start from? We started from time analysis, and we said we wanted to look at the time it takes, but then we didn't want that. We saw why we didn't want it, and we said, okay, let's settle on number of steps that the program runs. And then we saw that it will be a variable, and it's usually a variable on input size, which we take as n, which is the number of integers. Usually it can change slightly, but for now let's just say it's number of integers. And we said, okay, if the number of integers is n, which is kind of the input, then what is the number of steps, right? The number of steps can be very chaotic, right? If I have 2 nested loops, I could get an n square. If I have 3 nested loops, I could get an n cube, and I could have a two nested loop, and I could have a 3 nested loop, so I can have n squared plus n cube. That could be multiple things, right? So it's very feasible for my actual number of steps to be something like this: 4n cube plus 5n squared plus 6 plus 100n, some very chaotic thing. But what asymptotic analysis says is, if I have something, if the actual number of steps is something like this, right? 5n cube plus 4n square plus 100n plus, I don't know, 65, right? It's a huge term which I don't want to take this and go and look at all other programs and analyze things. But what asymptotic analysis says is, forget about all these guys. These are all small numbers. I don't care about them, right? Because all these guys will go away when n is large. Because what is kind of the leading term, which is the most powerful term, the powerful term is n cube, right? Because n cube is going to engulf all of these guys, right? Because n cube is always better than n square, like larger than n square when n is large, right? It's always larger than 100. Even if the coefficient is large, n cube will be greater than 100 after some point, right? And n cube is going to be larger than 65 after some point, right? So we don't care about any of these. And similarly, we don't care about this coefficient 5 as well, because it's a constant. I don't care about it's n cube or 2n cube or 3n cube. It's order of n cube, right? So all we'll say is, at the end, this is nothing but big O of n cube. Okay, and this is where we'll stop with asymptotic analysis. We have this convoluted expression. All asymptotic analysis does is give us an easy way to express the complexity of this code, and we'll say, okay, this is an n cube code. It's an order of n cube, or big O of n cube, right? And that's the main takeaway, right? So how will this n cube be? This n cube will be something like, for I equal to 0, I less than n, I plus plus, and inside that for j equal to 0, and inside that for k equal to 0 to n, right? So I have n into n into n will give me n cube. Yeah. And similarly, n squared will be 2 nested loops, or there could be many different ways this can happen. Maybe I have a recursion, many different ways this could happen, right? But all of that we'll stop all of that and say, oh, it's just n cube. I don't care whether it's 5n cube or anything. It's n cube, right? So that's basically time analysis, and the exact same thing works for memory analysis as well. What is memory analysis? Memory analysis is basically the amount of bits which are used by the code to run, right? I might have 5 different arrays for one's array, so then it's 5n, right? Maybe given an n, I have to create a 2-dimensional array, which is n cross n. So then the size is memory is kind of like n square, right? And yeah, I'll stop very soon. Don't worry. So it's the exact same thing. Everything goes exactly the same, and that just gives us space complexity, right? And that's basically do the exact same thing, but do it for space instead of the number of steps. Instead of counting the number of steps, we count the number of bits, that bits or bytes or whatever it is, because it's all constant factors away. It's just number of integers in a sense. It usually comes down to that, right? So that's space complexity. So that's all there is to this. Now let's look at some small, some more common complexities that we encounter in usual programs. So till now we saw big O of n, we saw big O of n square, we saw big O of n cube, and similarly any big O of n power c. All of these we call polynomial, right? And then we also saw big O of 2 power n, which is exponential, right? But between these there are many other things. Between n and n square there are a lot of other things, and two important time complexities are big O of n log n and big O of n square root of n, right? What is n log n? N log n is just n into log of n. Whenever we say log, we always say log to the base 2, right? And this is a very common complexity which you'll probably look at tomorrow in the first session, or I don't remember if it's the next session itself, sorting. So when you have sorting, n log n is the complexity of that, and you'll see why that is. And n log n falls between n and n square. Why? It's more than n because there is extra log n factor, but of course log n is less than n. N square is nothing but n into n, right? N square is n into n. Here it's n into log n. So n and n are same, but log n is less than n. So n log n is less than n log n. N log n is less than n square. Similarly, here I have n into root n. N and n are same, but root n is less than n. So n root n is less than n square, and it's more than n. And we also know that log n is less than root n. This is slightly more mathematical. I mean, it's nothing very hard. It's pretty, if you know, you can just do some basic math and you'll see this. So n log n is less than n root n, right? And yeah, so these are the, so n root n again comes in a lot of problems, which I think you'll see on day 3, I believe, when you come to some, it's called square root decompositions, and you'll see a lot of such things. Yeah, so Puneet, regarding base 2 and base 10, again, it doesn't matter. We usually almost always say base 2, but it doesn't matter again because it's just a constant factor away. Log a to the base b and log a to the base c is just the difference. The difference between them is a multiplicative factor of log c to the base b, and which is a constant. So we don't care about constants, right? So it doesn't actually matter if it's log to the base 2 or log to the base 10, but whenever you see log, it almost always means log to the base 2. Yeah. Cool. So I think we'll stop right there. So this is basically space complexity. I know I spent a lot of time. So typically I would have given a lot of examples, but I just felt it's good to give you an intuition of why we are doing this, rather than just going around giving a lot of examples. So to get more familiar with this, I would suggest you look at, there are a lot of questions like MCQs around on many online platforms. I'll try to give you some links as well. Just go there and try to figure out which is order n square, which is n cube, lots of examples of programs, and you try to find out what exactly that space complexity and time complexity is. I'll try to give you some links on which you can do this. But I basically wanted to focus on the intuition behind why we do this, and I hope that is kind of clear. And I've already extended by more than 10 minutes, or almost 10 minutes, and so let's stop here. I think your next session starts at 8. So yeah, so maybe have dinner and come back, or just stick around. Cool. So I couldn't look at a lot of your questions. I hope I saw Srikanth answering a lot of them. I hope most of them are answered. I'll be around on Discord as well to answer any more queries that you have. See you around. I think I have one more session with you day after tomorrow, I believe. I'll see you again then. Bye. Have a great workshop ahead. See you.